page 394. 11. Novarti's research findings are very important. Novartini, in a book published by Oxford University, discusses the problem of gaseous dispersion. It is a physical law that gas in a vacuum expands instead of contracts. Therefore, it cannot form itself into stars, planets, etc. That which cannot happen given any amount of time. Do you agree? If you agree, you are being scientific, for you are agreeing with scientific facts. If you disagree, you are fooling yourself. We will now assume that clouds form themselves into what evolutionists call protostars or first-generation stars. Stars exploding and supernovas producing heavy elements. The problem of the Big Bang only produced hydrogen and helium. Somehow the 90 heavier post-helium elements had to be made. The theories had to figure out a way to account for their existence. The theory, the first stars which were formed, were so-called first-generation stars, also called population 3 stars. They contain only lighter elements, hydrogen and helium. Then all of these stars repeatedly exploded. Billions upon billions of stars kept exploding for billions of years. Gradually, these explosions are said to have produced all our heavier elements. This concept is as wild as those preceding it. Another imaginative necessity, like all other aspects of this theory, this one is included in order to somehow get the heavier post-helium elements into the universe. The evolutionists admit that the Big Bang would only have produced hydrogen and helium. The nuclear gaps at mass 5 and 8 make it impossible for hydrogen or helium to change itself into any of the heavier elements. This is an extremely important point and is called the helium mass 4 gap. That is, there is a gap immediately after helium 4. Therefore, exploding stars could not produce the heavier elements. Some scientists speculate that a little might be produced, but even that would not be enough to supply all the heavier elements now in our universe. Among nucleides that can actually be formed, gaps exist at mass 5 and 8. Neither hydrogen nor helium can jump the gap at mass 5. This first gap is caused by the fact that neither a portion nor a neutron, a proton nor a neutron, can be attached to helium nucleus of mass 4. Because of this gap, the only element that hydrogen can normally change into is helium. Even if it spanned this gap, it would be stopped again at mass 8. Hydrogen bomb explosion produced deuterium or hydrogen 2, which in turn forms helium 4. In theory, the hydrogen bomb chain reaction of nuclear changes could continue changing into ever heavier elements until it reached uranium, but the process is stopped at the gap at mass 5. If it were not for that gap, our sun would be radiating uranium towards us. Quote, in the sequence of atomic weight, numbers 5 and 8 are vacant. That is, there is no stable atom of mass or mass 8. The question then is, how can the building up of elements by neutron capture get by these gaps? The process could not go beyond helium 4, and even if it spanned this gap, it would be stopped again at mass 8. This basic objection to Gamow's theory is a great disappointment in view of the promise and philosophical attractiveness of the idea. William A. Fowler, California Institute of Technology, quoted in Creation Science, page 90. Clarification: if you will look at any standard table of elements, you will find that the atomic weight of hydrogen is 1.008. Deuterium is a form of hydrogen with a weight of 2.016. Next come helium, 4.003, followed by lithium, 6,939, beryllium, 9,000.012, boron, 10,000.811, etc. Gaps in atomic weight exist at mass 5 and 8. But cannot hydrogen explosion cross those gaps? No. Nuclear fission, a nuclear bomb or reactor splits unevenly, halves. Uranium into barium and technetium nuclear fusion, a hydrogen bomb combines doubles, or hydrogen into deuterium, helium 2, which then doubles into helium 4, and stop there. So as hydrogen explosion, even in a star, does not go across the mass of 5 gap. We will now assume that hydrogen and helium explosions could go across the gaps at mass 5 and 8. 3. There has not been enough theoretical time to produce all the needed heavier elements that now exist. We know from spectrographs that heavier elements are found all over the universe. The first stars are said to have formed about 250 million years after the initial Big Bang explosion. No one ever dates the Big Bang over 20 billion years ago, and the date has recently been lowered to 15 billion years ago. At some lengthy time after the gas coalesced into the first generation stars, most of them are theorized to have exploded and then 250 million years later reformed into second generation stars. These are said to have exploded into third generation stars, and our sun is supposed to be a second and third generation star. 4. There are no population 3 stars, also called first generation stars, in the sky. According to the theory, there would be population 3 stars containing only hydrogen and helium, many of which exploded and made population 2 second generation stars, but there are only population 1 and 2 stars. Isaac Asimov, Asimov's New Guide to Science, 1984, page 35 and 36. Random explosions do not produce intricate orbits. The theory requires that countless billions of stars exploded. How haphazard explosions result in the marvelously intricate circlings that we find in the orbit of suns, stars, and binary stars, galaxies, and star clusters. Within each galactic system, hundreds of billions of stars are involved in these interrelated orbits. Were these careful balances not maintained, the planets would fall into the stars, and the stars would fall into the galactic centers, or they would fly apart. Over half of all the stars in the sky are in binary system, which 2 or more stars circling one another. How could such astonishing patterns be the result of explosions? Because there are no first generation population 1 stars, Big Bang theory requires that every star exploded at least 1 or 2 times, but random explosions never produce orbits. 6. There are not enough supernova explosions to produce the needed heavier elements. There are 81 stable elements and 90 natural elements. Each one has unusual properties in intricate orbits. When a star explodes, it is called a nova. When a large star explodes, it becomes extremely bright for a few weeks or months and is called a supernova. It is said that only the explosions of supernovas could produce much of the needful heavier elements, yet there have been relatively few such explosions. Throughout all recorded history, there have been almost no supernova explosions. If the explosions occurred in the past, they should be occurring now. Research astronomers tell us that 1 or 2 supernova explosions are seen every century, and only 16 have exploded in our galaxy in the past 2,000 years. Past civilizations carefully recorded each one. The Chinese observed one in AD 185 and another in AD 1006. The one in 1054 produced the Crab Nebula and was visible in broad daylight for weeks. It was recorded both in Europe and the Far East. Johannes Kepler wrote a book about the next one in 1604, and the next bright one was 1918, and the latest in the Veil Nebula in the Large Magellanic Cloud on February 24, 1987. Quote, supernovas are quite different, and astronomers are eager to study their spectra in detail. The main difficulty is their rarity. About 1 per 650 years is the average for any one galaxy. The 1885 supernova of Andromeda was the closest to us in the last 350 years. Isaac Asimov, New Guide to Science, 1984, page 48. Number 8. Why did the cellular explosion mysteriously stop? The theory required that all stars exploded often. The observable facts are that throughout the recorded history, stars only rarely explode. In order to explain this, evolutionists postulate that 5 billion years ago the explosion suddenly stopped. Very convenient. When the theory was formulated in the 1940s, throughout telescopes, astronomers could see stars whose light left them 5 billion years ago. But today we can see stars that are 15 billion light years away. Why are we not seeing massive numbers of stellar explosions far out in space? The stars are doing just fine, is the theory, which is wrong. Number 9. The most distant stars, which are said to date nearly to the time of the Big Bang explosion, are not exploding, and yet they contain heavier elements. We can now see out in space to nearly the beginning of Big Bang time. Because of the Hubble telescope, we can now see almost as far out in space as the beginning of the evolutionist theoretical time. But as with nearby stars, the farthest ones have heavier elements, our second generation, and they are not exploding any more frequently than are the nearby ones. Number 10. Supernovas do not throw off enough matter to make additional stars. There are not many stellar explosions, and most of them are smaller star-nova explosions. Yet novas cast off very little matter. A small star exploding only loses 100,000 of its matter. A supernova explosion